The global water crisis is an issue that affects people around the world. In fact, 1 in 9 people lack access to safe water resources. Lack of water can lead to sanitation issues, disease, and even death. However, there may be a solution to this crisis within nature itself. While there is only 2.5% fresh water on the Earth's surface, as compared to 97.5% salt water, membranes may allow for the significant use of excess salt water to impact the way people use water around the world. Membranes are thin, selective barriers that allow certain chemical species to permeate them while rejecting other species. The benefit of membrane desalination through the process of osmosis is that it results in less energy consumption. The principles of forward and reverse osmosis may be used to desalinate certain water sources and make them clean enough to be used in people's everyday lives. The objective of the reverse osmosis forward osmosis experiment is to evaluate the performance of different membranes under different operating conditions. Analysis of membrane performance examines the values of water flux, solute flux, salt rejection, and intrinsic salt rejection. A forward osmosis desalination process features a feed and draw solution. Forward osmosis uses high osmotic pressure gradient to achieve flux across the membrane. Osmotic pressure is a colligative property, and therefore high values can be achieved in a concentrated draw solution. The undesirable species is found in the dilute feed solution, possessing a low osmotic pressure. The draw solution pulls water from the feed across a semi-permeable membrane, diluting the concentrated draw solution. The draw stream will then undergo a solute removal process, leaving a clean water stream. Reverse osmosis is a pressure-driven process and requires a high energy usage compared to forward osmosis. A saltwater solution is purified as hydraulic pressure forces water through a membrane. The selective membrane rejects the permeation of salt, leaving a freshwater product stream. Osmotic pressure can be calculated using the Van Hoff equation shown above. The rate of salt diffusion out of the boundary layer, as dictated by the mass transfer coefficient, is dependent upon fluid flow characteristics within the membrane channel. Before beginning the experiment, various safety precautions should be considered. Like in any laboratory, it's important that experiment participants wear protective clothing, including gloves, lab coats, and safety glasses. It is critical that participants wear gloves to avoid fouling the membrane. Additionally, it is important to thoroughly check the setups for both experiments before beginning. The systems operate under pressure, so it is important that the valves are tightened and all lines are attached appropriately. Maximum pressure for the forward osmosis system is 10 psi. Forward osmosis procedure. Begin by preparing a 1 liter solution of 5 molar NaCl and use a stir bar to completely mix the solution. Place the stir bar in the blue feed tank and fill the feed and draw tanks with 2 liter distilled water. Turn on the chiller and make sure the water level is between the designated lines. Make sure all fittings are connected. Load the HTI TFC membrane into the cell with the active side facing down. It may be necessary to cut the membrane in order for it to not touch the outer rings of the cell. Place top half of the cell on top of the membrane and place the washers and nuts on the designated bolts. Tighten with the wrench in an X pattern. Start the data collection software on the computer. Turn the system on and let run for 20 minutes. Make sure to flush air bubbles out. This should allow the membrane to equilibrate. Set desired flow rate and pressure. For this experiment, flow rate remained a constant 1 milliliter per minute and pressure was adjusted from 4 psi to 6 psi and then to 8 psi. Calibrate the conductivity probes using solutions of different concentrations. Make sure both the metal bands on the probe are covered. 100 milliliters of the 5 molar NaCl solution to the draw tank. Let the system run for 30 minutes to equilibrate. After this time, record the feed conductivity and temperature. Again, add another 100 milliliters of the solution to the feed tank and let run for 30 minutes. Record feed conductivity and temperature. Add a final 100 milliliters of the solution to the feed tank and let run for 30 minutes. Record feed conductivity and temperature. Begin by turning off the system by turning off the pumps. Stop the data software and save. Drain each tank into the sink and refill with 2 liters tap water. Flush the system for 5 minutes and then repeat with 2 liters of tap water. Flush a third time with 2 liters of distilled water. Use a compressed air line to purge the system. Open the cell and dispose of the membrane. Repeat all steps again by changing the pressure to 6 psi and then to 8 psi. Reverse osmosis procedure. Begin by calibrating the conductivity probe using solutions of different concentrations. Make sure the metal bands are fully submerged. Make sure the water level in the chiller is between the designated lines. turn on and set to the correct temperature. Fill each cell with distilled water prior to adding the membranes. The first membrane to test is NF270. Load each membrane into each cell with the shiny side facing down. Place the top half of the cell on the membrane and load the designated washers and nuts onto the bolts. Tighten with a wrench in an X fashion. Record the mass of each of the graduated cylinders. Place the permeate outlet tubes into a designated outlet beaker. Fill the feed tank with 9 liters of distilled water. Make sure appropriate valves and fittings are tightened and connected. Set flow rate to 2 liters per minute and adjust pressure to 100 psi. Turn on the system and purge all air bubbles from the system for 15 minutes. The first run will just be with distilled water. Put all outlet tubes into designated graduated cylinders and start the timer. Stop the timer when 15 milliliters of permeate has been collected in each graduated cylinder. Record the mass of each of the graduated cylinders in addition to the conductivity of each. Take the conductivity of the feed solution. Then adjust the pressure to 150 psi and let the system equilibrate again. Once finished, you can repeat all the same steps. Additionally, you can adjust the pressure to 200 psi and complete the steps again. To test with a concentrated feed solution, create a 1 liter solution with enough NaCl to create a 2,000 parts per million saline feed. Add to the feed tank and allow 10 minutes for the feed to mix. Test using the same operating conditions. You can repeat the same procedure with the BW30 membrane and compare results. The experiment was concluded with an analysis of membrane performance that examines the values of water flux, solute flux, salt rejection, and intrinsic salt rejection. By looking at the reverse osmosis graph, it is clear to see that salt flux is greater for the NF270 membrane. Key findings to take away from this experiment include that in reverse osmosis, as the pressure decreases, salt rejection increases. For both reverse osmosis and forward osmosis, pressure increases as the water flux increases.